As we start into a whole new chapter, chapter 4, we're going to start to look at more and more applications of the derivative. And the first thing that we're going to explore is some graphical implications that can be found from the derivative. In fact, we can graph functions very robustly using the derivative and even the second derivative of a function. And so this is our first section where we're going to explore a few things here and some connections to a few things on graphs and some connections to their derivatives. So let's start with a whole set of definitions that we're going to use throughout this chapter and throughout our graphing of functions. So let's talk about extreme values, maximum and minimum values of a function, and some specific types of maximums and minimums. So we're going to have a function. Given a function whose domain is D, we define the absolute maximum of the function to be the point where the function is the absolute highest it can be on the entire domain. Mathematically, what this means is this statement right here, that a function has an absolute maximum at a point C if f of x is less than or equal to f of c for all x in the domain. So if that point, f of c, is the highest point on the graph, the absolute highest point on the graph that the function achieves, then it is the absolute max. And if we reverse that, the absolute minimum of a function, we say a function has an absolute minimum at a point C if f of x is greater than or equal to f of c for all points in the domain. So that's what it means to be an absolute minimum. So graphically, and I noticed on this function, I want to be clear that this function is actually going to stop here and here. So our domain will be on this range here on the x-axis that I have graphed. So if this function stops at these 2 points, what we have is we have an absolute maximum right here at f of b. So this point here, f of b, gives us an ordered pair that we would say, I'm actually going to write that as an ordered pair, not just f of b. This ordered pair b f of b is an absolute, and I will abbreviate, absolute max on this function, because that point is higher than any other point on the domain of the function that we're looking at. And this point right here, a f of a, is an absolute minimum point. So absolute, and that word absolute should sort of stand out. An absolute max or an absolute minimum means that it is the absolute highest point that the function achieves or the absolute lowest point that the function achieves on the entire domain. And that's what it means to be an absolute. These are the highest and lowest. You can also think highest and lowest values that a function takes on. So that's our first 2 definitions of extreme values. Now we also have what are called local or relative maxes and mins. Now local is what this textbook uses, but relative is also a word that comes up, and so I'm going to go ahead and have both of those definitions here too. So a local versus absolute, a local or a relative maximum at a point is if it occurs around an interval, in some open interval. If we say that it occurs in some open interval, another way to say that is to say near. And sometimes we'll hear that language. Near means in some open interval around a point. So if you have a maximum value, meaning that around some little interval, so if we kind of focus in, these 2 points that are highlighted right here are what we would call relative or local maximums. Now, this one in particular is obviously not the absolute maximum of this graph. It's not the highest point that is achieved. All these points up here are higher, a little over here to the left, but this point is what we call a local max, and this point here is also a local max. Now, interestingly enough, we're not talking absolute here, but this particular point right here is also the absolute. We could say it's the absolute and local. It can be classified as a local max, but also it is the absolute max. But what that means is on this little highlighted interval, that point is the highest point. Okay? So these red circles, they're called local maxes, local maximums, since they are the high points on the graph. Okay? They're actually we have a couple of them, and we can have multiple local or relative maximums. All right. And then the opposite is the minimums. So if we happen to have a low point, a local or relative minimum at a point, if the function is greater than f of c for all x in some open interval around x equals c. So again, when we say an open interval, that means near x equals c. That's another way to say that. So if we can look on both sides of a point and see that that point is the lowest point on some small interval, then we call that a local or relative. So both of these are local mins on this graph. These are both local mins. Turns out this one in particular, actually on this graph, is also the absolute min for this graph based on the way the arrows are going that we will continue up. Okay, so those are our definitions. So we're going to work with those definitions. So we've got absolute maxes and mins, the absolute highest or lowest point on a graph, and then we also have local maxes and mins. And finding these points will help us to guide the graphs, and we're going to explore that a little bit more with a few examples now. Okay, one quick note as we start heading into graphs and looking at restricted domains. Endpoints cannot be local maxes or mins. So let's just make a little point here, highlight this. Endpoints cannot be local maxes or mins, because to be a local max or a min, you have to be low or a high point on some open interval around, right? Near a point, meaning you have to be able to look on both sides of the point. So the x-coordinate, on both sides of the x-coordinate. And so with endpoints on an interval, you can't create an open interval. Endpoints, on the other hand, can be absolute. So endpoints can be absolute extreme values, maxes or minimums. So keep that in mind and make a note of that, and we'll use that as we go through. So now I just projected this graph on the board just to start with a visual. Grab this this little image, and we can look at this image and we can say, okay, let's find all of the absolute and local max and min values. So let's list them all out. So first I'm just going to graph them on here, look at them on here, and so what we can see is at this first I see a few points here that I'm going to identify, and clearly they're sort of labeled as well. And what we can see from this graph is that the absolute highest point that is achieved is at D. So we would call that the absolute max. And then the lowest point, and we don't have numbers here, we're doing it visually, but the lowest point that is achieved, and if it helps to pull out a ruler, we can see that that point is the lowest, right? Those are f of E and f of A are kind of close. So with my ruler, I can see that f of A is lower. So this is going to be my absolute minimum. So if I'm labeling, if I'm listing here, I would say that my absolute max is occurring at D and f of D, and my absolute min is occurring at A, f of A. So notice one of those actually was an endpoint of the graph, and the other one was a point just within the domain. So D was just a point within the domain. And then in terms of all of my local maxes and mins, so for local, let's do local maxes and then local mins. So for my local maxes and my local mins, those are occurring anywhere where we can create a small interval around, and I'll do my highlighter to show that. So clearly right here is going to be a local max. This is going to be a local min. This is going to be a local max. This is going to be a local min. And so we could say, and I'm just going to label these. If I want something to be an absolute max or min, I will include the word absolute. But from here on out, let's make a little note. Note. If no clarification is given, then we are referring to a local or relative. A local or relative max or min. Clarification will be given on absolute. So if I just say max right here, then we know that that is a local max. That's a local max, this is a local min, and this is a local min, rather than writing local on all of those. If I just say max or min, we're referring to the relative or the local maxes and mins. Right here, that we are both a local max and an absolute max. Now, this point down here, by the way, is the absolute min, but it is not a local min because we cannot create that interval with my highlighter. I cannot show that it is a minimum value on an open interval around A or near A. It's just an end point. So it ends right there. It can be an absolute, but it's not a local minimum at that point. Okay, so just some clarification on the definitions and how they work at the endpoints. So the local maxes, so let's go ahead and label those local maxes at B, F of B, and then of course at D and F of D. Looks like an A. D and F of D. And then we have our local mins at C, F of C, and just put a comma there, and at E, F of E. I'm going to run off the screen a little bit. Okay, so graphically we can identify both the absolutes and the local or relative maxes or mins. Okay, let's keep going and keep talking about a couple more. I want to talk about a few graphs that we know. So let's look at x squared. So what if we came across x squared? What would be the extreme values, the max or min values of x squared? Well, x squared, and I'm just going to do a real rudimentary graph right here. X squared is the graph of this parabola. So here's y equals x squared. And its domain, by the way, is all reals, or from negative infinity to infinity. I didn't restrict the domain. I just said discuss x squared. So if we wanted to talk about where we've got maxes and mins, both absolute and local, we can see right here that this point at 0, 0 must be the absolute minimum. This is the absolute minimum of this graph. It is also a local minimum, or just minimum if we want to drop that classification because we noted that up above. But it is a minimum value. It is the absolute minimum value. It is also a local minimum value because we can create an open interval and it is the lowest point on that open interval. Now, so if we were to classify here, we could say absolute min and just min value at 0, 0 for this function. There are no maximum values. This function, right, the arrows, x squared, this goes on, increases, grows without bound, actually at both ends of the graph. It does not ever achieve a maximum, absolute or local. So we have an absolute min or just minimum value, local min, at 0, 0, but there are no maximum values for this graph. Now, what about x cubed? Well, what about x cubed? What does x cubed look like? Well, x cubed is this cubic graph, y equals x cubed. And notice that on this cubic graph, there is no extreme values. There is no absolute max. There's no absolute min. This graph, right, runs from negative infinity to infinity across the coordinate plane. It never has a local max or min. There's no interval within here where we have a local max or min, a peak or a valley. We have none of that occurring here either. And so in this case, there are no max or min values, absolute or otherwise, absolute or local to be specific. I'll put that in parentheses. Okay, so there are no max or min values on this particular graph. Okay, let's think about what happens with some trig functions, because trig functions have some interesting behavior too. So let's take a look at I want to actually look at 2 sine of x in a variety of ways. I want to look at it first just on its domain from negative infinity to infinity, and then I want to talk about, well, what happens if we then restrict it and we look at it on some closed intervals, open intervals, half open, half closed. So let's do all of that with 2 sine of x. And so 2 sine of x is, let's just get it graphed here first. So 2 sine of x has an amplitude of 2, and a sine curve. This is going to be pi over 2, pi, 3 pi over 2, 2 pi, and so forth, negative pi over 2, and negative pi. Let's get our graph here. Should all be pretty good at graphing trig functions. Okay, so here is y equals 2 sine of x, and obviously this keeps going both directions. And let's talk about the absolute and the local max and min values on this curve. And it turns out that we actually have an infinite number of absolute maxes and mins, and we have an infinite number of local maxes and mins. Running off here. This is clearly a local max. There will be another local max over here and another local max over here. Here is some min values. These are obviously local values here and here. And these points are also, they are both local and all of them are also absolute. We have multiple absolute, so these are absolute maxes and local maxes. Okay, all of these are. This is an absolute max and it's a local max. This is an absolute max and it's a local max. Okay. Turns out because they all are achieving the same value, remember in that definition, I don't have it projected right now, but to be a local max at C, f of x just had to be less than or equal to f of c for all x in the domain. So the reason I rewrote that here is because of that equal sign. You can have multiple local maxes. We're hitting the exact same point at each of the exact same height. The function is hitting the exact same height at each of those points, and therefore it is giving us multiple, infinite, in fact, absolute maxes. Okay? All of them are also local maxes, but there are also an infinite number of local maxes. And on the same note, these are all our absolute mins or local mins, and this is obviously absolute and local. So when we go to list this, when we want to go and list what our absolute maxes are, and there are more than one, right? There's an S there. When we want to go and list that, what we want to say is that they occur at, for x values, pi over 2, but then they occur every time we cycle through a period of the sine of x. And so we're going to say plus 2 pi k, where k is an element of the integers, and the height that they achieve is actually 2, because this had an amplitude of 2. So the y value is 2. So absolute maxes are occurring when x is pi over 2 plus 2 pi k, and the corresponding y value there is 2. I am writing it as an ordered pair here. Those are our absolute maxes, but those are also local. So I'm going to put a slash here. So we have absolute maxes and local maxes at all of those points for the sine of x. Now let's talk about where the mins occur. So the local and the absolute minimum values, and again, there are more than one. Those are occurring, well, there's a couple ways we could write it. There was actually multiple ways we could have written the absolute maxes. I went with pi over 2. I'm going to go with 3 pi over 2 for x and then add 2 pi k, but we could also use negative pi over 2, right? So there are multiple ways to do this, but I am going to go ahead and start this. These occur when x is at 3 pi over 2, and every time we cycle through a period of the sine beyond that, so 2 pi k. And again, on those local and absolute mins, the minimum value that this sine curve, because of its amplitude, hits is negative 2. So the y values are negative 2. So we would write this as 3 pi over 2 plus 2 pi k, negative 2, where k is, again, an integer. And we can write k is an element of the integers. I wrote that as 2 boxes. I guess those are really just one answer, right? Or where do our extreme values occur? Okay. So that's when we look at the sine, 2 sine of x on the entire domain, which is from negative infinity to infinity. But what happens if we do some little restrictions? And so let's just run through these restrictions kind of quickly, and I'll just do real brief little graph so we have a visual. So we have the graph of 2 sine of x right there, but if we restricted it from just 0 to pi, closed interval. So here's 0, here's pi over 2. If we look at the sine, and here's 2 on the y-axis. If we look at this curve, just from here to here, give it a little bit better curve, where are, and the endpoints were included, so notice that I've filled in, I have points where I'm including those endpoints. Where are our relative or our local maxes and mins? Where is our absolute maxes and mins, or do they occur? So notice at this point right here that we have both a local, because there's an open interval that we could look at around pi over 2, where that is the maximum value. So this is both a local and absolute max at that point. So we could state that, so we know that we have both an absolute and a local max at the ordered pair, pi over 2, 2. Now what about absolute, local? Well, actually, let's list them as separates. Do we have absolute min values? Yes, we have 2 of them actually. The minimum values that are occurring, the absolute minimum values that are occurring on this interval are occurring at these 2 endpoints. So at 0, so we have and there's actually 2 of them, absolute mins. There's 2 absolute mins. They are occurring at 0, 0, and 0 pi. Now, what about local mins? They do not exist. There are no local mins. There's no open interval where we have a minimum value on this function. So we do not have any local mins, but we do have 2 actually absolute mins, and that is because they achieve the same low value at 0. Oops, I just noticed that I wrote my ordered pair backwards right there. That should be at pi 0. So that should be pi, comma, 0. Okay, let's look at just one more. I know I have a couple other intervals here, but what I would like to look at is, let's look at this particular one right here. Let's look at, I know we could go through and look at all of these, but let's look at one that has a half open, half closed interval. So let's take a look at 2 sine of x from negative pi over 2, let's zoom in a little, negative pi over 2 to pi over 2. Here's x and y and 1, 2, so the amplitude, and it's open at negative pi over 2. So down here at negative 2, we actually have an open circle, and then the sine curve comes up and then hits positive 2, and it's closed there. So we have a closed circle there, a closed filled in dot. We actually achieved that too. And so when we look at this in terms of where are our extreme values, where are our local, where are our absolute maxes and mins, turns out that we have an absolute max, and the absolute max is occurring right here. We actually have that value. But beyond that, we have no other extreme values on this segment of the sine of 2 sine of x because of the interval. Because we have right here, notice what's occurring right here is it looks like we want to say that's a minimum value, but we never achieve that minimum value. We get close to it, but it is not filled in. It's an open circle right there. So this is not a min. Okay, it's not a min in any form. It's not an absolute min, and it's definitely not a local min because we don't have an open interval, but it's definitely something that we would want to consider. We want to look at that and say, man, it looks like it is, but it's not. It never actually gets to that point. It never gets to negative 2. It's getting infinitely close to negative 2. Talk about limits, but it is not actually achieving negative 2. So what we would say here is we would say that we have an absolute max at pi over 2 and 2. In terms of the local max, there are none. They don't exist. And how about local mins? Well, also, those do not exist. And how about absolute mins? Also do not exist. Okay? None of these are achieved. None, no values where we hit these. Okay? So if we wanted to say state all of the extreme values, we would really just have this one where we have an absolute max at pi over 2 and 2. All right, and so we can play with those, restricting the domains. In the essence of time, I'm going to actually stop right there. But you could do the same thing, and you could look at what happens if you have both sides of the interval is open. What happens there? What if both sides are closed? What if we look at different little segments, right? And just really kind of practicing with these definitions. It's an absolute max or a min. If it's the absolute highest point that it achieves, that the function achieves on the domain that's given, restricted or otherwise. And it's a local max or min if it is on an open interval around that point, if we achieve a low value or a high value on an interval near that point.